So my report is about composite materials and about one interesting effect concerning waviness of the fibers. I'm going to talk about this type of composite materials, usually used for aerospace industry. About 50% of fiber fracture, and usually it has linear response when we have elastic stage of deformation. And it's very usual approach to get effective properties for composite material using this periodic cells of the material or representative volume element. And all of them usually looks like this. Some of them very short. The length of the fibers is not high. Some of them have a long direction in the direction of enforcements, but this is very usual approach. When we analyze experiments with composite material in longitudinal direction, in case of compression, we have results like this. So we have smooth decay of the stiffness, and the question is, what is the reason for this? And the idea of research is because we cannot get this from this small volume element. And the idea is to do very long periodic cell like this and add some waviness and to see what we have in this case. The waviness here is just this value, this angle. So the volume element looks like this. This is long enough. There are a lot of fibers, and the model is very simple. So matrix modeled as solid elements and fibers as a beam elements. It's just a rendered a thickness or sections of beams. And we can avoid all margin effects, and the material is quite simple. We can run a lot of this model. The problem is maybe the waviness is increased when we do curing of the composite materials. This is the problem. So some pictures here how composite plate can be curved after manufacturing. And we have model how to model the curing. Here are some equations. So the matrix is changing during the manufacturing regime, and then we can recalculate it to composite materials. The main idea is that if we consider, for example, cross-ply layup, we have the most highest residual stress in this case. So during manufacturing, we have some layers in compression along the fibers. So here is the plot for during manufacturing, how compressive stress looks like during time. So they are relatively high. And taking into account this stress, we produce curing of this periodic cell. And the question is that the growth of the waviness less than 5%. For any, you see initial waviness here. So for any initial waviness, no significant growing of the waviness. So we can neglect this effect. Now we can do numerical experiment with this cell. So we have, for example, tension and some initial waviness. And this is the composite for what we use properties. And this is the data from manufacturer. So it's for For tension, we have just straight lines, and if we have high waviness, we have lower value of the stiffness. And in case of compression, it's very interesting result. So if we have no waviness, 0 degree, we have straight lines. I would say if we don't use finite strain theory, we also have straight lines. And if we use finite strain theory and we have initial waviness, in these cases, we have this smooth decay of the stiffness. And this 0.5 degree looks well suited for manufacturing data for this composite material. And it's very interesting fact that we have different standards to determine compression Young modulus. And for this curve, 0.5 degree of waviness, we determined, we obtained using these standards, using this curve, Young modulus. And you can see that 141 gigapascals, it's a tensile modulus. For some standards, you have the same value, but manufacturers, they said that it's 128. We have one standard that gives us 125, but it seems like they used this one standard and the most conservative value. It's very popular in aerospace, this standard. So we believe that they use this one, and the waviness is 0.5 degree. Okay. And the next question is how to model it in the real practice. We need continuum model, and the question is, can we, for example, put into elastic equations some nonlinearity here? Is it remain elastic still if we have here some nonlinear coefficients? And to resolve this, we can write down potential in this form. And then we can write down constitutive relations according to this potential. We have everything like as usual, but we have this interesting multiplier. And we can ask for this multiplier to be equal to nonlinear coefficient that we want. And in this case, we have this equation, and it can be always resolved with these initial conditions. Yes. And here are some examples of these compliances from these curves that I showed before. And we can approximate them by cubic polynomial functions. And here, for example, how it looks like. We did the same before for shear coefficients, but the reason was that matrix materials is nonlinear, and when we apply shear, we completely involve into deformation of the matrix material. So we can use it to capture this nonlinearity. For example, it's a compression experiment with a hole plus minus 55 degree layup, and here the modeling result, here experiment, but here we have damage. If we add damage, we can capture completely this curve, and it's interesting when we use nonlinear elasticity, the damage looks different in this case. But for continuum equations, our main conclusion probably is that we can implement nonlinearity in all diagonal coefficients, and the equations is still elastic. And another thing that we can add some sensitivities to stress state. For example, here it's a shear curve with some additional loads. and we have they look a little bit different. So using combination with this potential, we can capture this effect further. So that's all. Thank you for your attention.